So we're going to continue our discussion of Java parallel streams and internals by talking about splitting, combining, and pooling. And some of this will be a little bit of a recap from sequential streams, which is perfectly good, although there's some nuances and subtleties you have to be aware of when you program with parallel streams. So as with sequential streams, a parallel stream's splitting, combining, and pooling mechanisms are largely invisible unless you choose to influence them in some way or another. So again, it's like the ninja, which is not going to be seen by the naked eye unless you're really observant. As we mentioned before, all the Java collections that come out of the box with the Java class library have splitterator methods defined on them, and that can be used to create parallel streams. As you can see here, we have a splitterator, which is inherited from the interface collection. Given a default implementation, actual concrete implementations of collections typically override that splitterator to do whatever is necessary to split things evenly and efficiently if possible. And then there's also the parallel stream factory method, which looks almost identical to the sequential stream factory method, the difference being that the true parameter is passed as the second parameter to stream support.stream to get it to be a parallel stream, as opposed to the false parameter, which is what's used by the stream factory method. There's also a bunch of collectors. A bunch of them come out of the box. There's collectors here like toList, toSet, toMap, and these are all going to create what are called non-concurrent collectors, which seems like a bit of a misnomer, but it turns out that non-concurrent collectors work perfectly well with parallel streams as with sequential streams. We will talk later about what a concurrent collector is and give you some examples of how and why you might want to use them or implement them. And then the third piece of the puzzle, which we're going to spend a bit more time on later, is the common fork join pool. And that's used to run all those intermediate operations on chunks of data that have been split by the splitterator. So that's really where the rubber meets the road. That's where parallel computations are taking place, and that's done in the common fork join pool. And again, that's done deliberately. We use the common fork join pool because the more work you can put into a common pool, the better the underlying work stealing algorithm of the common fork join pool will maximize processor utilization. That's the name of the game, maximizing processor utilization. So by dumping everything into that common pool, it actually gives more things to be stolen to keep the processor cores humming along in maximally utilized ways. As with sequential streams, you can customize these mechanisms as you see fit. There's the splitterator interface, and as we saw before when we talked about sequential streams, you can use splitterators in order to basically advance your way through the elements one at a time sequentially, but there's also additional stuff that's added with parallel streams. So try advanced is used both for sequential streams and for portions of the parallel stream. Once you get to a point where you no longer want to split things any further, then try advance is used to process stuff in a single thread. But the really interesting part of parallel streams is the try split method. And the try split method is the one that's used to partition a chunk into a pair of subchunks. And that process occurs recursively till you chunk everything up into atomic sized chunks, where you no longer have a way to split them, either because you don't want to split them any further, even if they have multiple elements for whatever reason, or you've got yourself to a single element, and so you can't really split it any further because it's like, trying to divide, it's like trying to do like, the wisdom of Solomon. You don't want to cut the baby in half, right? You got it to a point where it's perfectly atomically sized and you don't want to reduce it any further. So try split is the really workhorse method in splitterators for parallel processing. Likewise, there's this thing called a collector, and you can have these different factory methods here like supplier, accumulator, combiner, and these are all used to take elements in a stream, be it sequential or parallel, and then join them back together again. And we will talk in more detail about what collector does and how it works. It's a really cool capability. We kind of glossed over it for the sequential streams discussion, but we will cover it in more detail for the parallel streams discussion. So we just talked about splitterators for the splitting phase. We talked about collectors for the combining phase. What can be done with the applying phase? And it's only a few things you can do. And the main thing you can do in the applying phase is leverage something called a managed blocker. And a managed blocker is a way of being able to manage the number of threads that are used in the common fork join pool in order to be able to maximize performance. And this is really only important if you're dealing with I/O-bound processing. So that raises the interesting question. What does it mean to be I/O-bound processing versus something else? Well, the two types of processing are compute-bound processing, sometimes called CPU-bound processing, and I/O-bound processing. So what's the difference? So compute-bound processing are operations that don't do I/O. So a good example would be checking to see if a number is prime, or computing the greatest common divisor, or searching a string that contains a work of Shakespeare to find phrases in that work of Shakespeare. Those would all be compute-bound operations, or sometimes called CPU-intensive or compute-intensive operations, because there's no I/O required. You're just looking at stuff that's in memory. What would be the opposite? I/O-bound operations. What are some examples? Reading or downloading the contents of images that are reachable through their URLs. So in that case, you're going to have to go out there, or the Java class library code will go out and open up a connection to a remote server, download the contents of that URL, store it someplace, probably write it to disk. You could store it in memory, but eventually if it gets written to disk or flash memory or whatever your storage is, your persistent storage, that will also be an I/O operation. So things that involve network communication, things that involve reading and writing to the network, things that involve reading and writing to files that are local on your computing device, those are all examples of I/O-bound operations. Why does it matter? Well, it matters quite a bit because I/O operations will block. If you try to download a large file, then there'll be periods of time when you're waiting for the next chunk to show up. Or if you're writing to disk, there'll be periods of time when the thread is blocked waiting for the write to complete or a read to complete or whatever. And during those periods of time when a thread is blocked, it's not doing anything else useful. So the reason why we use things like managed blockers is because when a thread blocks, then if we're not careful, we can quickly underutilize the CPU and the cores, because while the thread is blocked, there's other work that could be done, but that thread is dedicated to doing nothing but waiting or blocking at that point, at least for so-called synchronous I/O, which is the default in a lot of the code we're looking at. So what the managed blocker does is it says, if you're going to block, then that's an indicator to the common fork join pool to temporarily create another thread to compensate for the fact that the current thread is going to block. And that other thread could be used to schedule other operations to run, thereby increasing the amount of utilization of the system, which is always the name of the game. We want to make that CPU and the I/O devices really sing for their supper and do their work. So we're not trying to give them any rest at all if we possibly can. So that's what a managed blocker does. We will talk more about managed blockers later, but they're very important to be able to increase the size of the common fork join pool, at least temporarily, until the number of threads that are blocking goes away or is greatly reduced, in which case the threads that were created to compensate for blocking threads will be terminated by the common fork join pool.